Look at this animated diagram. We have raw data points, a student's name, a roll number, a GPA, floating aimlessly in a blank void. In simple linear programming, you track these individual variables one by one. If you're building a system for 10 students, you can manage that. But scale the system to process 30,000 unique individuals, and maintaining those isolated, unlinked variables quickly turns into an unsustainable, tangled mess. To solve this scaling problem, developers use object-oriented programming. This approach binds raw data and its associated actions into a single, repeatable package. The foundation of this system is the Python class. A class is a template, an architectural blueprint that dictates exactly what an object will be before any concrete is actually poured. Mastering classes moves a developer from a typist struggling to juggle chaotic variables into an architect designing scalable, logical systems. Taking that blueprint and constructing a building is called instantiation. This is the moment an abstract class sparks into physical memory as a tangible object. The instant you create that new object, a specialized automated builder kicks in. In Python, this is the constructor method, written as __init__. It immediately springs into action to assign the object's baseline attributes, like setting the specific name and GPA for a brand new student. This diagram shows a master blueprint routing instructions to two distinct objects. Notice the recursive loop inside each one. That loop represents the self parameter. It forces the newly built object to reference its own unique internal data, ensuring student A's grades never overwrite student B's. Once that internal state is set, it requires protection. We call this encapsulation. A solid perimeter forms around the object's core attributes, so outside code cannot accidentally alter them. Python handles this security through syntax. By prefixing an attribute with double underscores, you trigger a process called name mingling. The system intentionally obscures the attribute's name to the outside world, locking the private data down. Through the initialization of the init method and the strict boundaries of encapsulation, a well-built object becomes a secure, self-sufficient fortress, ready to interact safely within a larger software ecosystem. Imagine expanding your system. You have a reliable general design, but you need a new object that behaves slightly differently. Redrawing an entire architectural blueprint from scratch for every minor variation wastes time and memory. This animated tree diagram illustrates inheritance as the solution. Here, the core structural traits of a central parent class, let's say a generic animal, flow directly down to a child class, like a dog. The child automatically adopts the parent's attributes without writing redundant code. But a dog barks. It requires a specific sound. To handle this, the child node can swap out that generic behavior for a uniquely shaped alternative. This is method overriding, redefining an inherited method to provide specialized custom action. Specialized actions are highly effective, but developers also need their methods to process varying amounts of data. A calculation function might need to add 2 numbers today, but 5 numbers tomorrow. Classic compile-time method overloading is not natively supported in Python. Instead, developers simulate it. By using default parameter values or the *arg syntax, a single method can flexibly accept any volume of incoming data. Combining inheritance and overriding allows a software ecosystem to evolve organically. You preserve your core architecture, avoid repetitive coding, and execute highly specific behaviors seamlessly. At this point, our objects are secure, specialized, and flexible. But to achieve their full utility, they must integrate directly into Python's broader mathematical and logical rules. Python achieves this native integration using magic or dunder methods. These special functions, enclosed in double underscores, allow custom objects to hook directly into Python's built-in syntax. For example, the dunder str method translates raw object data into a clean, user-friendly string when requested. Meanwhile, the dunder repr method outputs an unambiguous, strict representation specifically meant for developers reviewing the code. Look at this diagram of 2 distinct abstract shapes representing completely custom vector objects. Because of a magic method called dunder add, these shapes can be added together using a standard plus sign. We call this operator overloading. Operator overloading takes static data containers and transforms them into dynamic entities that respond to the natural laws of your code. A standard math operator adapts instantly, cleanly merging complex structural data on command. Python classes serve as the architectural engines for modern software. They allow developers to build scalable, intelligent, and deeply integrated digital worlds, one code object at a time.